Hello everyone, welcome back to Astronomy and Cosmic Earth. This is the second video of our time travel series in which we will see interesting fact related to time travel, exploring the scientific theories that make this mind-bending concept possible. Buckle up as we journey through the physics of time travel and uncover the mysteries of space-time. Time travel has long been a staple of science fiction, captivating our imaginations with the possibility of journeying to the past or future. But what does science say about the feasibility of time travel? To understand this, we need to delve into the fundamentals of modern physics, starting with Einstein's theory of relativity. Einstein's theory of relativity, introduced in the early 20th century, revolutionized our understanding of space and time. According to his theory, space and time are not separate entities but are intertwined in a four-dimensional fabric known as spacetime. This concept forms the cornerstone of our exploration into time travel. In the realm of general relativity, massive objects like stars and planets cause a curvature in spacetime. Imagine spacetime as a flexible fabric. When you place a heavy object on it, the fabric bends. This bending of spacetime affects the motion of objects, including the passage of time itself. This phenomenon is known as gravitational time dilation. Gravitational time dilation means that time runs slower in stronger gravitational fields. For instance, near a massive object like a black hole, time would pass much more slowly compared to a location further away. This effect, although minute in everyday life, has been experimentally verified through precise measurements using atomic clocks placed at different altitudes on Earth. But what about traveling through time? One theoretical possibility involves wormholes. A wormhole is a hypothetical tunnel-like structure that connects two separate points in spacetime. To understand the practicality of wormholes, we must consider their stability. Current theories suggest that wormholes, if they exist, would be extremely unstable, potentially collapsing upon entry. Moreover, the energy required to stabilize a wormhole, preventing it from collapsing, is beyond our current technological capabilities. Another intriguing concept is the closed time-like curve, or CTC. A CTC is a path in spacetime that loops back on itself, theoretically allowing an object to return to its own past. While the mathematics of general relativity permits the existence of CTCs, their physical realization remains highly controversial and poses significant paradoxes, such as the famous grandfather paradox. The grandfather paradox questions what would happen if a time traveler went back in time and prevented their grandfather from meeting their grandmother. This would mean the time traveler would never have been born, creating a logical inconsistency. Such paradoxes highlight the complex and often contradictory nature of time travel within our current understanding of physics. Despite these challenges, the study of time travel pushes the boundaries of our knowledge and fuels advancements in theoretical physics. Concepts like quantum mechanics and the quest for a unified theory of quantum gravity may one day shed light on the feasibility of time travel. While time travel remains a theoretical possibility, our journey today has revealed the incredible intricacies of spacetime and the profound impact of Einstein's theories on our understanding of the universe. Join us next time as we delve deeper into the mysteries of time travel, exploring quantum mechanics and other mind-bending theories. Don't forget to like, subscribe, and hit the bell icon to stay updated with our latest videos. Until then, keep looking up at the stars and wondering about the infinite possibilities.